right, you guys, welcome to the penultimate set of notes for this semester. Penultimate is one of my favorite words. It just means second to last, but apparently we needed a fancy word to be able to say that. So I use it at every opportunity, clearly. We're going to be talking about gas laws. You guys already did a POGL talking about gas laws, and so we're just going to formalize some of those definitions, and you guys are going to do some practice. Like I said before, we really are finishing up about 2 units shy of where I would have liked to be, just because of the schedule of online learning and finishing a week and a half short and all of those types of things. But I just wanted to expose you to a little bit of gas laws and solution stoichiometry so that you have that at least a little bit in your brain if you go on to take more chemistry classes in the future. Okay, so gas laws were developed somewhat individually. We saw Boyle's law, and if a gas at a constant temperature is existing in a system, it's inversely proportional to the pressure. And that just means that if the pressure goes up, the volume will go down. So you can see in this image the same amount of particles in every single scenario. And we start out with a little kitten. The little kitten is not applying very much pressure because he doesn't weigh very much. And so there's the volume of 2. And then we have maybe a full-grown cat, and that cat's heavier, so it applies more pressure and squishes it down to a volume of 1. Then we have a big fat cat, and that cat squishes it down even farther and squishes it down to about 1/2. So if pressure increases, you get a fatter cat, then volume decreases. So the equation for that is pressure 1 times volume 1 equals pressure 2 times volume 2. Using this equation is very straightforward. So if we have an example where a diver releases a bubble of 0.25 liters, and then somebody at the surface measures the volume of that bubble when it gets to the surface of the water, and it's 0.75 when it gets to the surface, what's the pressure that the diver is experiencing under the water? So at first glance, it kind of looks like we don't have enough information because we have a volume 1, a volume 2, but we don't have any pressures. And so what we need to do is just assume that the pressure at the top of the water is atmospheric sea level pressure. So we're just going to assume it's 1 atmosphere. Once we have that, we have 3 out of our 4 variables, and so we can solve for that 4th variable. So here, plugging in volumes and 1 atmosphere for the pressure, and I'll divide both sides by 0.25, which gives me 3 atmospheres. Charles' law is another law that depicts a relationship between volume and temperature. In this case, the pressure is constant, and so if you increase the temperature, then you'll increase the volume. So that's why if a balloon heats up, it'll expand and get bigger, and sometimes it will pop because it can't expand its volume anymore. So in this case, there's a relationship because they're directly proportional. We end up with volume 1 over temperature 1, volume 2 over temperature 2. If we want to do a Charles' law example, we can look at a 2-liter system at 25 degrees Celsius, and if the temperature is raised to 100 degrees Celsius and the pressure is constant, then we can predict what the volume will be. This is just a reminder to make sure you're always doing these calculations in Kelvin, because if you're not doing these calculations in Kelvin, they will not come out right, which is a bummer for sure. Okay, so Charles' law. We're going to plug in our numbers, and that puts us at, we have 2 liters divided by 25 Celsius plus 273. That's going to get us to Kelvin. And then on the right side, we have the second volume. And 100 degrees plus 273 to bring that into Kelvin. So then I've kind of simplified it down here. So we have 2 liters divided by 298 Kelvin equals volume 2 divided by 373 Kelvin. I want to get volume 2 by itself, and that's why I went ahead and multiplied both sides by 373 Kelvin. And when I do that, I get volume 2 is equal to 2.5 liters. Next relationship that's important is Gay-Lussac's law. And the pressure of a specific amount of gas at a constant volume is directly proportional to its absolute temperature. So P1 over T1 equals P2 over T2. An example of this is if we are measuring the amount of gas inside a container of fixed volume. So the volume cannot change. The thermometer reads a pressure of 248 torr at 0 degrees Celsius. What is the temperature when the thermometer reads a pressure of 345 torr? So I can use my P1 T1 over T1 equals P2 over T2. And the first thing I'm going to do is plug in my variables. So I have 248 torr divided by 0 Celsius plus 273 so that I have Kelvin. And then that's equal to 345 torr divided by P2. So now, because this T is on the bottom, I need to get it into the numerator so that I can solve the problem. I don't want to leave it down in the denominator. So to take care of that, I'm going to multiply both sides by T2. So these guys cancel out on the right-hand side. T2 cancels out T2. And on the left-hand side, now we just have T2 being multiplied by the rest of the left-hand side. If we simplify that, that means we have T2 times 0.91 torr per Kelvin is equal to 345 torr. At this point, simple division, divide both sides by 0.91, and that will leave us, oops, the bar goes away at the bottom, it leaves us with 397.78 Kelvin. The combined gas law was something that scientists developed because they realized that most systems involve changes in all 3 of these things. It's hard to hold all 3 of these constants. So they were like, all right, let's squish these together into one law. So what we can see here is that pressure and volume are both directly proportional to temperature. So pressure is directly proportional to temperature, volume is directly proportional to temperature. And so this allows us to create a relationship that kind of summarizes their, their relationship. A relationship that summarizes their relationship. I'm crushing it today. Anyway, so we'll have pressure 1, volume 1 divided by temperature 1 equals pressure 2 times volume 2 divided by temperature 2. This guy is pretty straightforward to use. We have a gas occupying 0.85 liters at 1 atmosphere and 27 degrees Celsius. We want to find the final temperature. If we change the volume to 0.65 and the pressure to 865 torr. So one thing that sticks out to me right away here, in addition to needing to turn my Celsius into Kelvin, which we always need to do, is that I have 2 different units for pressure. I have atmospheres for pressure and I have torr for pressure. And it doesn't really matter what unit of pressure you're using as long as they match each other. So you could turn 865 torr into atmosphere, or you could turn 1 atmosphere into torr. I happen to know off the top of my head, because I'm a nerd, that there's 760 torr in 1 atmosphere, so I'm just going to do that because I know it off the top of my head. All right, so I've got my starting amounts, 760 torr times 0.85 liters divided by 27 degrees Celsius plus 273 to get it to Kelvin. 865 torr times 0.65 liters over temperature 2. This is another scenario where you need to multiply both sides by T2 because, I decided to simplify first. But you'll still need to multiply both sides by T2. So you can go ahead and simplify this, right? So I've multiplied everything and added everything that needed to be added. Now I can multiply both sides by T2. There it is. And that's going to get that variable out of the denominator. Now we have T2 times 2.32 torr times liter per Kelvin, and then that all is equal to 562. If I divide both sides by 232, then I get 242.35 as my temperature. The last law that is important in our understanding of the behavior of gases is called Avogadro's law. So the volume of the gas at constant temperature and pressure is directly proportional to the number of moles. So if you have the same number of moles of gas in a volume, they are going to be the same volume no matter what their mass is. Okay, so even though helium only weighs 4 grams and oxygen weighs 32, they're at the same temperature and pressure, so they have the same volume. And this is the relationship that allows us to really be able to use the gas law to find out things that are useful to us. So when we combine all these things together, we get what I like to call PIV-NERT, which is pressure times volume equals moles times the constant R times T. PIV-NERT. PIV-NERT is on your cheat sheet. And basically it's just saying that all of these variables that impact the behavior of a gas are related by this constant R. So the gas constant is a universal constant, meaning it's true for every ideal gas. And remember, for our purposes, we're assuming all gases are ideal. So the most important thing about R is to check your units. Typically, we'll be dealing with R in liter atmosphere divided by mole Kelvin. And so that value is going to be 0.082, and I usually just say 821. I don't say 8206. It's like so much more effort. But there's a lot of different units you can use. The other one you'll possibly see in this class is liters torr mole Kelvin, which is 62.36. But I really try to focus on this top one. Because that's the one I have memorized just through years of use. And we don't use torr that commonly anymore, so the top one's a little more practical. All right, how do we use this ideal gas law thingy? So how many moles of gas are in a 3-liter vessel filled with oxygen at 750 torr and 25 degrees Celsius? I just need to plug in my variables. I'm going to change my torr to atmospheres so that I can use my atmosphere constant for R, but you could use the torr constant if you wanted. So 0.99 atmospheres times 3 liters equals moles. So I left that as in because that's my variable, times 0.0821 times 298 multiply it out, simplify 0.21 moles.